Okay, hello again, everyone. So this is going to be a working session looking at quantum effects in the context of our models. And some of what we will probably do here, well, we'll see what happens. People say, oh, do you get quantum mechanics in your models? Well, we know that we get many features of quantum mechanics, but we want to get some of the, we want to make sure we get every feature of quantum mechanics. And we don't know whether to get every feature of quantum mechanics, we first have to understand what electrons and things are, or whether we can get these features of quantum mechanics at sort of a bulk level. As I've said many times, one of the surprises of what's happened in the last few months has been discovering that a lot of things that I thought we were going to have to go to the particle level to get, like interpretations of energy and momentum and so on, have been possible to get at a bulk level. So let's see whether we can get quantum mechanics at a bulk level as well. So I'm going to go ahead and share my screen here. Great. And right. Okay, so Jonathan has prepared, let me make this a lot bigger. We're going to concentrate, I think, at first on the double slit experiment on Bell's theorem. Okay, so the double slit experiment, let's just recall what that actually is. So the idea is you have two slits and you have you shine a single photon at these two slits, and then you keep shining more photons at these two slits, and eventually you build up an interference pattern that just looks like the classic, a wave interference pattern, even though the things that you were sort of firing at the slits were just photons. At least that's a way to, and so we're sort of, but in a sense, that description kind of speaks about particles. So we have to see to what extent we can understand that. So Jonathan has a multiway system here, which he claims, and I still need to understand how this works, that he claims has some relationship to the double slit. So let's try to understand what this is. So this is saying, I'm not really understanding this. So this is basically saying that we start from a state here where we just have a photon tooling along, and then we are making a transition to a state in which it went through the left slit or in which it went through the right slit. Is that right?
Yep, that's the idea.
And then here, it's just propagating along saying, I'm a happy left slit photon. Okay, so then the question is, so this is what's happening at the level of pure quantum states. So in our model, when you make a quantum observation, when you have a quantum observation frame that is like the analog of an inertial frame, you'd be seeing a superposition of these two states because our quantum observation frame would be just slicing across right and left here. Okay, so now let's see what is happening here. So this is, the two branches are causally disconnected. Isn't this the same picture? Oh, I see what you're saying. Oh, okay. This is showing, okay, so this is a good picture. So this is showing the, this is showing the causal connections between these different situations. So it's saying that there's a causal disconnection here where this is the right slit, the photon went through the right slit story, and it has causal connections to these other, to the later history of that photon, but it doesn't have any causal connections over to the left here. Okay, so now the claim is that if we were to add this completion, okay, so the system as we have it right now, A goes to L, A goes to R, L goes to whatever, is not causal invariant. But we can add a completion that does make it causal invariant. So let's see what that does here. Okay, it makes something more complicated, and I'd like to understand this. And then we get this much more complicated thing. All right, so let's try to understand the interpretation of this. So, okay, question is, how do we sculpt? I mean, in our usual way of thinking about this, we need two things. We need causal invariance, because otherwise we're not going to get sort of a unique quantum reality and so on. And we also need to know how we're going to sculpt our quantum observation frame to capture different kinds of behavior. So, since Jonathan is the one who's gotten us so far, let's ask about those two questions. So
Okay,
first,
okay.
go ahead.
Yeah, sure. Sorry. So on the causal invariance question, I think we have a reasonable picture for how that kind of works in this context. So the idea is, as Stephen was saying, if we go back up just to the pure multi-way evolution graph that we had above, where you just have these two completely disconnected branches of history, as Stephen was saying, you as an observer are foliating this evolution graph, and so you are seeing superpositions of these two different of the states on these two different branches of history. But if you as an observer want to perform a definitive measurement, a measurement with a definitive outcome, somehow you have to be able to see these two, the two elements of the superposition as being the same. And so, what the minimal way you can do that is by defining an equivalence relation that says, the L state and the R state look to me the same. And so, the way that we can represent that in the context of these models is we have a pair of rules that says L goes to R, R goes to L. And then, but then the point is that in imposing that equivalence relation, you produce these kind of phantom states, these states that aren't really states in the underlying multi-way system, but they are emergent states that appear because of the equivalence that you have imposed in attempting to perform a definitive measurement. And it's those additional states that cause your representation to be causal invariant, even though the underlying representation wasn't causal invariant.
Okay, this is partly your interpretation of quantum mechanics, which is not a necessary feature of what's going on here. I mean, that's the observer has made that correspondence, as opposed to that correspondence exists in the underlying system, and the observer is merely sampling some feature of it through a quantum observation frame.
Right. So yeah, and we have various sort of explanations as to how the two approaches are at some level equivalent. This quantum observation frame idea is a more relativistic way of thinking of the same thing, where you're saying you're sculpting out something like a coordinate singularity, and then these completions, these things that say these multi-way states have to reconverge, become basically the analog of gravitational lensing of curved geodesics in the multi-way evolution graph. It's a different way of thinking about effectively the same idea.
Okay.
Sorry, go on.
No, well, so should we look at this one in terms of quantum observation? I mean, so in this is, okay, first of all, let's just check. This is causal invariant, right? With the completion here, by definition, it's causal invariant, right?
Right.
So if we say this, and we say here, causal invariant Q, I mean, it was a completion, so it better be. It's true, right?
Right. But if we did that with the original one, obviously it would be false.
Right. So how do we understand this? Okay, so let's say we're making a measurement here. We want to know, I mean, I'd really like to see this for a more complicated case where this thing isn't just two slits, but where we can actually see kind of the interference pattern, so to speak.
Well, this is the interference pattern, would be my conjecture.
What is the thing with the R's and L's here?
Yeah, right. So the underlying representation just has a pure photon goes through left slit, photon goes through right slit. But if you want to make an observation, you introduce these intermediate states, these sort of RRL, RL, RLL things, where the photon effectively goes through some combination of the left and right slits. And so those intermediate states, again, as you say, at least in my interpretation of this, are the interference states. And if we kind of aggregate those, they will produce something like an interference pattern.
Okay, so let's try to do that. Okay, so the first question is, if we were to feed, if we were to weight these edges, what would we see here? Right, we could do a weighted multi-way graph here. We're not going to see. So, I mean, one thing we should mention to people, I mean, by using a string substitution system rather than a hypergraph system, we're already taking we're already toying this thing quite a bit. But I think it's useful to do this because we don't have to, for example, here we might be able to deal with a one-dimensional space fairly easily from our string structure rather than having to build the space as well as building everything else. So let's take a look at this. Let's look at the most naive thing I can imagine, which is here. Just say, if we go to like 6 steps or something, we'll have a big complicated mess here, right? But now the first thing I might ask is, in the multiway system, I just like to understand what is the distribution of L's and R's and whatever as we get here. And I don't really know how to understand the LLRRR, what that means, and whether really we should be saying, you know, how many L's, how many R's, or what it is. But let's see what happens here. So what we're trying to do here, if I were to just say this, I would just get the state that comes out, right? So I'm getting out the thing that's coming out here. So, I mean, again, you know, this is the life of toy models. How we map this onto the real line is not completely obvious to me. I mean, I think, I mean, let's imagine that we are padding. Well, let's just take the last element there, and let's just make, okay. And now we want to do the LR distribution, so to speak, for each one of these. I don't know how this is necessarily going to help us, but let's just see what this does. So we've got now the distributions of counts of L's and R's for each of these things. And, well, let's do a counts of this again. Oh, yeah, that's kind of obvious that there's well, okay, so there are a few here where sort of it's binomialed up, if you understand what I'm saying.
Right.
Many of these, I mean, if we just make a histogram here, yeah. All right, I just want to do the power version of this, okay? So let's take this thing here. I'm just curious what this looks like. And we're going to do, like, say, 10 steps. And then I want to do, I mean, remember, this is a deeply toy model. Characters of that. And then, okay, so let's take the last of this. That was the final state. And let's take characters of that. And let's take, what do we do here? We mapped counts, and then we had counts of the, we had, whoops, counts here. Okay, and now we want to take the histogram of that. So this is now the, I mean, again, it's not clear that this is actually doing anything interesting, but this is just asking how many times each of those, yeah, I mean, this is kind of uninteresting. But what I want to understand is, so we've got one of these things that is the output of, okay, so we've got something like this. That's a big, long output of all the different states that can occur, right? So what we need is a quantum observation frame that says we're going to measure some particular part of that collection of states.
Right.
Right? Without the completion, we know that we're going to just get that. Right? So that completion is what is leading to what we're describing as interference. So maybe we should also understand, we also have a curvature effectively in this space. What is our kind of uncertainty principle curvature, so to speak, that comes because we don't have, let's take a look here. So this is the structure of the space. So if we, let's just look at this space in a slightly more understandable way, hopefully, maybe not, I don't know. Let's say states graph structure. So we're just looking at the structure of that space. And let's go a few more steps. Oh, gosh. It is really a bit scary that even the toyest of the toy model already is producing stuff like this. Okay, so what that is trying to do, so let's look at branch hill space here. That might be interesting to see. Yeah, what do we think that's going to look like? So we're looking at the what the heck does that mean? It's interesting how connected it is. It's also interesting that there are two different, I mean, it's almost like we're seeing them. So what this is telling us is that this is a map of the entanglements between quantum states here. So let's look at how that works as a function of time here. So let's look at how that is evolving. All right, what is our interpretation of this? So one question would be,
it's not maximally entangled, which is interesting.
Well, it's very entangled. I wouldn't say it's maximum. I mean, this is not a complete graph by any means.
Yeah, exactly. So it's not maximally entangled.
Oh yeah, okay. You said it's not maximally entangled, right?
Yep. Which is not obvious. I would have thought it would be very close to being maximally entangled.
So what do we think in the traditional, so, you know, let's say we're using just some kind of position basis, which it's not clear how we get that out of what we're looking at, but were we to use some kind of position basis for representing the results of this thing, what would the entanglement map look like for that? What do we think that would look like?
I mean, wouldn't a position basis just be laying out vertices in order of, you know, left to right character appearance?
Yes, I think so. But I mean, my question is, so maybe we should do that in this case. Maybe we should at least label, let's put in the labels here, at least up to level 6 here, and let's just take a look at what they are. Okay. Ooh, interesting. Okay, so what this is showing us is the rightmost, the right thing is sort of antipodal to the left thing.
Yeah, it almost lays out in position basis automatically.
Yes, quite. I mean, these are the most interfered cases, which interestingly, in our interpretation here, they don't, you know, they're not connected to each other. But so what we need to understand is this is a trivial quantum observation frame that was used to get this branch hill graph, right?
Right.
The question is, what are some more realistic quantum observation frames that one might use to measure the results of this experiment? And what branch hill graphs? Because what we think is going to happen is, well, we also need to look at this with weightings, right? We need to look at the weighting.
Yeah, in fact, hang on. I've just sent you some code.
Okay.
I don't know how to interpret this yet, but it looks interesting.
Okay, no idea what this is. All right, let's take a look at this. So this is
the weighted evolution graph for this system.
Okay, can we draw the branch hill graph weighted? Because I think that's going to be instructive.
I don't think I ever implemented a weighted branch hill graph. Let me just check.
Well, we had, I used weighted branch hill graphs in the technical introduction somewhere, so we must have code. Let's take a look here. String systems, that looks like a weighted branch hill graph. Okay, how did I do those weighted branch hill graphs? Let's take a look here. Oh, I have a function called weighted branch hill graph.
Right. Yeah. I mean, so you always have the option include state path weights.
Okay. Well, let's.
But that's not a weighted. That's not a weighted branch hill graph in the same sense that evolution graph is a weighted evolution graph. because these are path weights for each state, not multiplicity weights for each edge.
But isn't that what we want to get? Wait a minute. There's a path weights. These are the weighted. I mean, this is what I wanted to see, is where.
Okay, yeah, fine. Yeah, then you can just say, yeah, include state path weights true.
In what? In this?
In branch hill graph, yeah.
Okay. What does it include? Path? What?
It includes state path weights. So every vertex is now weighted by, every state vertex is weighted by the number of distinct evolution paths.
Okay, and how do I then display that?
Yeah, then you have to get the property value out.
Okay. Well, let's do that. Can we get the property value and make the vertex size be proportional to the property value?
I think that's what your code was doing earlier.
I know, but it didn't have the labels in. Well, maybe it did have the labels in.
That was branch hill graph structure.
Yeah, okay. That is very wild, complicated stuff there, but let's put this in. Okay, so this is that. And we appear to need, okay, so let's put in this thing here, where we say this is the graph, this is the rule, and we start off with A, and I have no idea what those weird things are there. But let's go 1 to 5 here. And
those look like size multipliers.
yes, they are size multipliers. But I don't know why I've got those labels there, which, oh, I see. Labels, vertex labels are vertex weight. Okay, fine. So what I actually want is vertex labels is, I'm going to just have vertex labels to automatic at the end here. Let me just not use any of this complicated crud here because I'm weighted branch. Which thing is calling which thing? I'm totally confused here. Oh, I see. This has to be, I see. We need vertex labels. All right. Well, let me go ahead and just hack this completely and just have vertex labels are automatic by default. Let's just have no ifs, just have vertex labels to automatic. And then let's rerun this guy. Okay, so now that's giving us the path weights. So that's telling us, in this case, just based on path weights, what we would expect the magnitude. Now, I don't understand the relationship between the amplitude and the probability here for these, because what we're getting here on each edge, we're getting an amplitude basically for that quantum state, because we're expecting that the combination, see, I'm not quite sure how that's working. Do you think you understand how that works?
So on each edge?
No. I'm saying that on each the result here.
Each vertex is weighted by its path weight, i.e. the number of distinct evolution paths that yield that state.
Indeed. But so my question is, when we are looking for, in the traditional quantum mechanics version of this, there's an e to the is going on each of these, going down each edge of this multiway graph, right? And I'm trying to understand what the analog of that, in this incredibly simplified model, what's the analog of that complex number? You see what I'm saying? I mean, this is supposed to be a representation of the wave function, basically. This is the wave function as a function of quantum states.
Right. But hang on, maybe I'm misunderstanding the question. I mean, so the natural metric induced on the multi-way causal graph is the complex number metric, right? When we ascribe coordinates to every state in the multi-way causal graph, we ascribe them with complex numbers.
Yeah. Okay, but so write down for me. So in this case, what we've got is this is showing the size of these red dots is basically the support in branchial space of, it's the measure for this point in branchial space.
Right. So so as I was saying, so we have a natural measure defined on all points in the multi-way in the multi-way causal graph, and so those state path weights act as a multiplier for the complex numbers that are the coordinates, and those yield the amplitudes.
All right. So in particular, what is the amplitude for RR here, given some arbitrary number for each edge? So let's imagine that our edges, we're sort of imagining there's an IH bar edge somewhere here. So what is the actual, what do we think the actual number the amplitude number that should be associated with this is?
Well, whatever its complex coordinate is multiplied by whatever its state path weight is, which we're not rendering anymore, but we can see it's large.
Okay, but so let's be concrete. Okay, so so you're saying in this branchial space, there is a coordinate location, and we are by convention, so to speak, treating this as the complex plane effectively.
Right.
So in a sense, the coordinates in this branchial space, and we don't really know whether they lay out as a Cartesian, this is just an arbitrary graph layout. So to say that they're Cartesian, who knows?
Well, no, the point is that we have freedom to choose the coordinate system, and that's the notion of different quantum observation frames. Different people observe different amplitudes, but the results of quantum measurements will still be preserved, or the time-like ordering.
Two issues here. We've got which foliation this is. That is, this branchial graph comes from a flat foliation, essentially an inertial foliation of the multi-way graph.
Yes.
It's not self-evident that this is the only quantum observation frame.
No, it's not. That's exactly what I'm saying. So in the same way as different inertial, or as different reference frames in relativity, transformations between them are described in terms of transformations of coordinate systems. Exactly the same thing is happening here. So the coordinate systems that define the amplitudes will differ for different quantum observations.
Okay, so you're making two statements here. First of all, this actual picture might look different. And second of all, the actual coordination within this picture is kind of arbitrary.
Well, those are kind of the same statement.
I know they're the same statement. Yeah. I know they're the same statement. I mean, you're saying the factor of 2, choosing our coordinates to be a factor of 2 larger, we could do that. We could also slice the multi-way graph in a different way and end up with a different branchial graph in which the position in the branchial plane, we can call it, given that we're rendering everything in a plane here, which may or may not be the right thing to do ultimately. I mean, it isn't the right thing to do ultimately. I mean, we're projecting a Hilbert space basically into a plane, which is right. a very coarse thing to do. But nevertheless, we get to actually make explicit pictures, which is very useful. Okay, so here, so explain to me, if we're going to compute the amplitude for each of these quantum states, right? We're saying there is a location in branchial space that corresponds to effectively complex coordinates in the complex plane. And then there is also a weighting that comes from the path weight.
Right.
So specifically then, what do we think, what would be, I mean, it's just write down explicit, let's make this function in the complex plane, so to speak. And we don't really know how this should be laid out, but let's assume that our branchial distances, again, this is going through several layers of stuff. So this graph layout is trying to map the branchial distance onto a Cartesian space, which ultimately it isn't a Cartesian space, but that's an approximation. So my question is, what should be the amplitude that we associate with this thing here?
Right. Okay. I mean, so obviously we have the coordinate choice is arbitrary, so we can just pick some coordinate vector that is that state. and we can
Fine.
just multiply that coordinate vector by whatever its state path weight is.
Okay, but let me be concrete here. Let me take this graph. Okay, I've got that graph there, and I'm going to ask for, I don't remember how to do this. Let's see, annotation values. Is that right? How do I get out the
path weight?
What's that? No, I'm trying to get out the coordinates, the vertex coordinates. Can I do that? That's extremely unuseful. Well, I can certainly say graph embedding. Okay, well those are the coordinates of the if I get the graph, the vertices, those are the coordinates. So you're telling me as a first approximation, I can just make those into complex numbers.
Right, right.
Okay. But now that's the position in branch Hill space. But then what is, and you're claiming that the contribution to the wave function is basically that complex number multiplied by the path weight. I haven't completely understood that. Why?
Well, so what would happen is, okay, so for a given branch-like hypersurface, which is what we're viewing here, we set a bunch of, we assign each state a coordinate, which is just a vector in some Hilbert space, but normalized so that they are all, their moduli are all one over the total state path weights for all the states in that branch-like hypersurface. And so then to get the particular amplitude for any individual state, we just take that coordinate and we multiply it by its particular state path weight. So that gives us a normalized measure that has the same algebraic properties as a probability amplitude.
Okay, but I'm not quite understood yet why. Okay, so we can actually do that for this case, right? So we just have to take, how do you go from a re-m? Let's see, I want the inverse of re-m. What's the inverse of re-m?
Is it not just complex? If we do complex,
yeah, we can probably map complex onto that. And just say complex triple at %36. Yep, there we have it. Okay, so those are the complex numbers that we get from the embedding of that graph. And then we can also get the path weights. But this is going to give us, so what we're going to get here in the end is laid out in branch Hill space. Okay, so what this is doing is for every LLL, RRR, whatever, in this incredibly simplified model, we're getting the quantum amplitudes basically, right?
Right.
Okay, so let's do that. We can compute. So then in what we had before, we should be able to get the quantum amplitude for each one of these L's, R's, whatever thing.
Mm-hmm. Right.
Okay. I mean, the thing that's still bothering me is let's walk through what is involved in doing what do we think the measurement really looks like? Okay, so we've got this thing, it's got okay, when we do a measurement, so we've got some detector that is measuring the right-hand side of these slits, okay? That is supposed to correspond to some quantum observation frame, right? In particular, it's most likely going to slice out its version of what is now frozen in time is something that might correspond to, for example, this region of branch Hill space.
Or probably anything where there are any R's.
Maybe. That's a bit unclear to me. And I mean, this is the problem, that we made a somewhat toy model. So it's not completely clear what, I mean, you're suggesting that we have a quantum observation frame that just picks out things that have R's in them. Well, everything has R's in it except the LLL things.
Right, right. So the only state that doesn't interfere at all with an observer positioned at the right slit is LLLL.
Fine, but what we'd like to be able to get is, as we move the observer down, down the line, so to speak. We want to be able to, they are going from a quantum observation frame. I mean, that is where we have the freedom, basically, to insert the position of the observer is, you know, what is their quantum observation frame? How does it slice through this branch shield graph? Now, really, it's not slicing through this branch shield graph at all, because this branch shield graph is merely a branch shield graph that we got from a flat inertial frame, so to speak. And the true situation is that we will be differently foliating the original multiway graph.
Right. But obviously that foliation will just correspond to a curved foliation in which the pure R state is at the bottom of the sort of curvature basin.
Yeah.
And the pure L states are not at all curved, and everything else is somewhere in between.
All right, but let's understand physically what that means. Okay, so we've got an observation frame in which we are effectively more or less freezing time for every R state. Right, that's what we're talking about, yes?
Right.
So what that will mean is, I mean, in terms of the sort of appearance of the thing, I probably got a picture here.
When you say every R state, you mean just the pure R state?
I'm not sure what I mean yet.
No, because I mean, okay, maybe I've completely misunderstood what's going on here, but I think what's going on is the pure R state is frozen. The things which contain a combination of R and L states can still move through time, but their progress is retarded by the fact that only the L states can move through time, so to speak.
Okay, so what you're expecting is that we have essentially a tipped frame, and we should try and draw the foliation, right? Because what we're going to get then, in a picture like this, if we were to lay out the multiway graph here, which we can do, we've got the multiway graph somewhere here, somewhere up here. It's a very ugly multiway graph, but we can, let's just take this multiway graph, okay? And let's lay that out in, yeah, let's layer that multiway graph. Oh my gosh. That is in the category of completely unuseful. That is a mess. And I have to say that this model is pretty minimal as these things go. What does this look like if we actually include the labels? Oh my gosh. It's a pity that this thing isn't symmetric between L and R. And I wonder if there's any way to force it to be that way.
You mean the embedding?
Yeah, the embedding.
Right.
Yeah.
I was going to say, I think the multiway evolution, it should be.
All right, so what we're talking about here is a quantum observation frame that foliates this multiway graph. So you're claiming that we could have an R freezing foliation.
Right.
That is forced by the partial order that's defined by this multiway graph to have certain structure with respect to the L's. Mm-hmm. Right? So it freezes on the R's. So what is that? What is that? So what does that correspond to? That in traditional quantum mechanics, that is projecting onto some eigenstate that corresponds to the R eigenstate somehow.
Exactly. So you know, our minimal notion of measurement is that it's an orthogonal projection in some C-star algebra, and so because it's a projection, it's therefore idempotent, which means it can't, you know, repeated application of it doesn't change anything. So this is analogous to the concept of freezing time around that particular eigenstate, which is what this frame is doing.
Okay, so we have a frame that freezes time around that eigenstate, and then the very freezing of time around that eigenstate implies something about the extent to which time can or cannot be frozen around other states.
Right.
In the way that, for example, we see in a structure like this, where we've frozen time around something here, but that has implications for the other parts of the foliation. So one of the things that we just don't have a good technology for right now, I mean, these foliations were drawn in a very complicated way. So what we would like to be able to do is to try that, to put a foliation in there that is a frozen foliation here, and ask what possible foliations are there that that have that constraint. I think we need Max for this, but Max is unfortunately still not available, but will be soon, hopefully.
Right.
Yeah, this is a Max problem.
But the point is, okay, so now if we have a detector at the right slit or the left slit, and so effectively we seal off all the pure L states and all the pure R states into coordinate singularities, then from the point of view of that quantum observation frame, this multi-way system will look like the uncompleted multi-way system. It will look like one in which the photon either went through L or went through R, and there's none of these interference states will appear.
Okay, let's understand that. Okay, so your claim is that if we freeze this, we will never get to see the freezing of that will also prevent, under time evolution, the interference states from occurring. Because your claim is, by the time, if we block it off right here, right? If we block off the evolution right here, nothing in the future light cone of R, the future kind of multi-way light cone of R, will ever show up.
Or yeah, I mean, or in other words, the future light cone or the future entanglement cone of R has all of its edges pointing only towards R states. They're tipped such that they only point towards R states, and none of the L states are causally accessible.
Well, put a different way, I mean, by the time you've frozen the foliation around R, you never get to populate. You never get to walk down these edges. Like the foliation has already got stuck here.
Right.
Therefore, the entanglement, I haven't started talking this way yet. The future entanglement cone, which is just like the future light cone. The future entanglement cone of R is not populated, or it has not been explored, so to speak. In that frame, you're not exploring the future entanglement cone of R.
Well, yeah, I mean, the point is there are two different ways in which you can get effectively the same results, right? That you can either say that it's like R terminates at a normal form, so it's like R is a singularity.
Mm-hmm.
But you can also just as well construct an event horizon that just seals off all the pure R states.
Yeah, exactly.
Which is not quite the same thing, because
okay.
in the latter case you still get evolution. It's just it's pure R evolution, and everything else is causally inaccessible because it lies outside the future entanglement cone.
Okay, so this is now, we just froze R here. We just had a way to freeze R. Actually, we did a bunch of other things too, which were not so helpful. But I mean, that's what you're talking about. But this has, now we don't in fact want it to go to anything else, right?
Well, that's okay. We can just say we know that X and R, X just means there used to be an R there. So that's the example. That's the singularity case.
Wait a minute, I'd like to see that singularity better, where R just ends up in a normal form and nothing else. I think we can do that by just taking out all of, I mean, it's a very boring case here, but we just take out all of these, R-related transformations, right?
You could also just do, A goes to lower. Okay.
Yeah, there we go. I mean, that's an example where, yeah, it's still full of X's though. Did you have a better way to do this?
Yeah, right. Okay, so if we go back to the original multi-way system, but you just add an additional rule that says A goes to lowercase r.
Here?
Right, well, I mean, anyway, it's a join.
I can see that. Yeah. And what's that going to do? With the R goes to X included?
Well, I mean, no, you can get rid of that. Yeah, the original multi-way.
Yeah, but this is just going to be a third branch, right?
Right, but it's one where time freezes.
For sure. Right, but so okay. All right, so let's go back down here. So what we've got here, I'm still trying to understand the relationship of the, so what we've got is something where we should be able to generate a wave function as in RL space, effectively, where the coordinates of the wave function, just like we have psi of x, in a traditional Schrodinger equation story in the position basis, we would have, psi of x, where x is a parameter of the wave function. Here, our parameter of the wave function is this RL string, correct?
Right. We could even construct, I don't know if this is going to be useful, it's just an idea. I mean, we could construct a coordinate system where, it's two elements. The first is the number of L's, the second is the number of R's. We can just see how the amplitudes vary in that with respect to that coordinate system.
Sure. We could, I mean, look, this question about how, I mean, we could also have a three-dimensional coordinate system where we have RL and blank, basically. But yes, I agree with you that what we've got, I mean, essentially what we have here, what we're ultimately getting, these things here are effectively, psi of string. Each of these dots represents psi of string. Now, the thing I haven't completely understood is the relationship between the location of psi of string in branch Hill space. That there are two things here, and I think you need to explain them to me again. Okay, there's the branch Hill coordinate that we were representing, at least I was representing. I don't know whether you have used this notation. I'm so keen on this notation. A version of a vector in branch Hill space.
No, you berated me the other day for using boldface Y as my branch Hill coordinate.
Oh, okay,
thing,
fair enough.
Which is probably a bad choice.
Yeah, okay. This was my cutism for, in ordinary space, right? Vectors would be X with a vec above them, and this is kind of the analog of a vector because we're dealing with a much wilder space here. But okay, so we have the B coordinate, right? We have two things. We have the weight and we have the B coordinate, and you're trying to tell me what the value of psi is, how we deduce the value of psi from looking at this picture. So tell me that again, because I didn't understand that.
Right. Okay, so the point is that most of the conditions that we actually care about on amplitudes are conditions on the norm squareds, right? For things like unitarity, that's ultimately what we care about. So what I'm saying is that those conditions, the norm squared conditions, are given by the state path weights. They're given by the things that are weighting these nodes. Then everything else, all of the geometrical information that's not encoded in the norm squared, is then just a more or less arbitrary statement about the coordinate system used for laying out these states. So you have a direction in branch Hill space, and then which is given by a complex vector, and then you weight that by the state path weight.
So what you're basically claiming is the abs of the psi squared. So essentially the abs of psi squared is that is the story of that is basically a story of path weights.
Right.
Whereas to get some finer detail, you are using the branch Hill coordinate. And I don't fully understand. I mean, I understand the branch Hill coordinates can be thought of as being in the complex plane, but I don't understand the relationship between the branch Hill position and, for example, the arg of psi. So, for example, what other properties should be true? What we're saying, and what I'm a little bit confused by, is when two things are nearby in branch Hill space, what is being said here is that the value of psi is nearby. Well, it may not be nearby because the abs may be different, but the phase is similar.
Right.
Which is exactly what we expect, because in the path integral interpretation, what we're seeing is that this is nice, actually, because in the path integral interpretation, what we're seeing, a path is coming down the multiway system. And what you're saying here is the phase is determined by the turns of that path, so to speak. The path integral is is measuring the turns in that path. And this is showing where did the thing land up, which can be mapped into its phase, basically.
Right. So if you consider the overall multi-way evolution graph, and you think about a ray from the initial state up to the state you care about, that can be characterized by an angle, right?
Sure.
And so then if the states are kind of adjacent or nearby in the branchial
All right,
hypersurface,
I'm buying it.
that the angles are nearby.
Yeah, I'm buying it. That's actually very nice. So basically, the claim is that the phase, I mean, what we're seeing here is that the phase, it's actually very nice, right? The phase is basically the e to the I, s over h bar or whatever, the whole thing. And that phase, I mean, the phase is the result of integrating e to the I s over h bar down the multiway system.
Right.
And so that is quite nice. That is quite nice. And the separation, which is actually a bizarre separation that I hadn't really appreciated before, between, maybe I did, but between the absolute value and the phase is interesting. All right.
And I think it's actually, I mean, okay, my personal feeling is that that's basically a notational convenience that has become accepted as a fundamental postulate, but isn't one.
Well, in other words, your claim is that really it's like the merging of space and time. This would be an interesting conclusion, that that basically is it merely a convention that the magnitude and phase of the wave function are packaged together?
Right. Right. So yeah, I mean, the fact that you can store both as a single complex number doesn't indicate that they have to be related.
That's very interesting. That's very interesting. I mean, that certainly would have. I mean, honestly, that's interesting. I mean, that's a piece of confusion in quantum mechanics that goes back a long, long, long way. If that's really right, that those two things should be broken apart, that wrong turn was taken in 1925 or something.
Right.
Because that's been that way ever since then. And it is interesting that the path integral doesn't talk about the magnitude of the wave function.
Right, right. And similarly, measurement outcomes don't talk about the phase, because I think they're fundamentally different things.
Well, that's interesting. That's really quite interesting. So, okay, so let's go back. All right. So given that understanding, it makes sense to think about the position in branchial space, even this rather arbitrary layout, as corresponding to phase. So if we think about that as phase, then we're still the mapping between, we've got this map of phase and magnitude. Well, at some level, you would be claiming something which is not working perfectly here, is that your interference patterns would be that the darkness of the interference pattern is just the size of these dots, because that is the norm.
Right, exactly. So one of the reasons it's not quite working here is because we have states of varying length.
Yeah.
I think that's possibly one of the reasons why it doesn't look quite right. I suspect if we actually filtered out the branchial graphs so that they were all of the same length, we might get something that's more convincing, but I don't know.
I think this is way too toy a model, but we'll see. Let's take a look. We can do it. Okay, so let's take this branchial graph. Are these graphs? Yes, they are. Okay, so let's take that branchial graph, for example, and let's just take, okay, so let's say filtering for fixed length. So we want a subgraph here, if I'm not mistaken, of vertex list of, oh gosh, I've got to call this graph something. Okay, let's say a subgraph of GGG, where it's the vertex list of GGG, where it's the select that with string length. Pick your string length, 4.
Yeah, okay, let's try 4.
Hard to interpret. I don't
This might be
understand
too
that, but
small a
let's
case.
try. Let's just try for the hell of it. Let's just try string length S, and let's just make a table of the string lengths, just in case something interesting happens. What's the maximum string length? 6. Let me just make those small. Well, that's at least fun, that one.
That's an interesting structure, isn't it?
It is an interesting structure. All right, let's try a bigger graph. Yeah, Calais on this live stream is pointing out the bar graph was basically the interference pattern. You are correct. Yeah, I mean that was, but the problem was we didn't know what the x-axis was. That's the difficulty here. That pattern up above was, well, I don't actually know what that is. What is this? What is this?
So these are the evolution weights. So
I know, but in what ordering?
By vertex name, which is not edge name.
Anyway, so let's try and make this a more sensible version, okay? Because what we should be able to do is that edge weight, we can get the property list for. Okay, so hold on. Let's get this thing here. Evolution of that is this, and then we want the. I hate using property. Property, I do not believe in property. What is the new name for property?
It's deprecated, isn't it? But I can never remember how we were meant to do it.
I think it's annotation value.
Okay, that would make sense.
Okay, so there are the edge weights. Okay, so what we want to do then, those are the edge weights. That's what you had before. So what we have actually is annotation value.
By the way, heads up, this is an evolution graph, so there are step numbers in the state, in the vertices. So it'll be a list of an integer and then the string.
Wait a minute, wouldn't we want to take the last then of this?
Yes, we do, probably. But wait, hang on. The last of the evolution graph?
No. That's
we want to take the last layer, right? Which would be, that's kind of what we were doing.
It's an evolution graph weighted.
Yep.
What is that graph then? So this is, let me just look at a smaller version of this.
Sure.
Okay, so that is an evolution graph. Very ugly evolution graph, I would say. Why is it so ugly? I think that's a bug. Because I think it didn't use it's not using its layout, proper layout.
Well, I mean, I just set it to be layered digraph embedding.
But why is it looking so ugly relative to what the evolution graph looks? Oh, it's not a states graph.
Yeah, exactly. I think if you just do regular evolution graph, it'll also look ugly.
But why isn't this a states graph? And why is there a difference between those two anyway? I mean, couldn't we have do we have a states graph weighted? No, we don't, because
we don't.
of closed time-like curves and other such pathologies.
Exactly. This is weighting of edges really only makes sense in the evolution graph case.
Okay. All right. Fine. All right. So what you're saying is potentially, if this is an interference pattern, then many hats should be eaten. I don't believe this. that this is, it's going to be something like this, but it isn't exactly this.
Right,
That's
but
what
I mean,
we're trying to.
yeah, it's a good point though, that we might be able to get something if we take the evolution graph weighted and we take a graph difference, so we only get the last layer.
Yes.
And then we only look at those edges. We might be able to. I don't know if we can get anything sensible out of that.
Well, we should be able to get the weights for those. Why aren't we just picking the things on the last layer, right?
Yeah. I mean, we can do that.
Pick the things on the last layer.
We have the time steps. What am I talking about? Yes. Good point.
Do they have time steps in them?
Yes, because it's an evolution. If you look at the vertex list, you'll see each state is actually a list containing a step number and the state itself.
Okay, that's easy. All right, so then let's okay, so then what we want here is, in this particular case, we would take the original evolution.
Oh, and conveniently, they're laid out in the position basis, sort of.
Yeah, well, maybe. Okay, so hold on. Let's get. Actually, the most interesting thing here, which maybe you had realized all along, but I had not realized, is this business about the fact that the path weight gives the norm of the wave function, and the position in branchial space gives its phase, which actually is kind of obvious from lots of other stuff we've looked at.
Right.
But
right.
was not as clear to me.
Right. I mean, so the analogy is one. I mean, it's perhaps useful to make the analogy with general relativity, where if you're thinking about geodesics, the field equations only tell you about the dispersion angle of geodesics, or you can interpret them as telling you about the dispersion angle of geodesics, right? In the same way that the path integral only tells you about the phase of multiway geodesics. But in conventional general relativity, the intensity of the geodesic, the intensity of the light ray, is kind of completely unrelated to that derivation, and the analog of an intensity of a null ray or something is the amplitude in the multiway evolution graph.
Well, okay, so let's walk through that again. I mean, if you have a bundle of geodesics, no geodesics go missing in standard general relativity.
Right.
Like the bundle survives. In a multiway graph, it's more complicated because the bundle isn't. The bundle can remerge and so on in ways that it cannot. Well, but actually, that's not so obvious because a bundle of geodesics in our, let's see, is that obvious? It's not totally obvious to me that a bundle of geodesics represented in.
I don't think it's about merging. It's about, okay, if you just consider the pure space-time causal graph, you can have multiplicities of causal edges, right? That's not an issue.
Yeah.
And you can also have multiplicities of edges in the multiway evolution graph, which is what we're computing when we consider the evolution graph weighted.
Yes.
But the point is, in the same way as our derivation of GR doesn't tell you anything about the weightings, about the multiplicities of causal edges, only the dispersion angles of geodesics, but not their intensities. The same thing is true in the multiway case. That the path integral is telling you about the dispersion angles of branchial geodesics, but it doesn't tell you anything about the weights, about the multiplicities of the edges.
All right. So given that idea, okay, let's talk about quantum mechanics and its. I mean, then the claim has to be made that sort of destructive interference in quantum mechanics, which we can sort of see in these pictures down here. Okay, your claim is that the destructive interference that's happening for this thing here, where the norm squared is small, that the main freedom that quantum mechanics has is the routing of which thing got destructively interfered. That is, that the bundle of things coming down the multiway graph had to go somewhere. That's unitarity.
Right.
Right? And the only question is, where did it go? And if the interference fringe, so that's a very different interpretation from, in classical electromagnetism, where, you also have those interference fringes. You are really not thinking about it that way because you're really thinking about the phase of, the vector potential or whatever. I mean, it's a different view. in classical electromagnetism, it would be completely wrong, I think, to separate essentially the polarization from the, I mean, yeah, what are we talking about here? We're effectively talking about polarization versus intensity, aren't we? Phase.
Yes, right. I think so.
And the claim is, I see. And in classical electromagnetism, those things are really intimately connected. You really can't have, there isn't a unitarity notion where you're just getting, I mean, there must be some, well, the Poynting vector gives you the energy flux. I'm now confused because there is obviously a conservation of energy. Mm-hmm. So I'm a little bit confused how that works. But okay, but in this case, what you're saying is the total intensity guaranteed to be 1 just by the nature of these edges in the multiway graph.
Right.
So in a sense, whereas what you're effectively doing is scrambling where the GD6 went in whatever basis you're using for the observation, you're scrambling the position of the GD6. So destructive interference is the GD6 got routed away from that position in the basis that you're using.
Right.
Okay, let's go back and look at what's happening here. Okay, so we've got edge weights. So what we want to do, we have the original evolution. So here we're going to select those things. We're going to do cases of this, and then let's, oops, very wrong thing I just did. I somehow just told it to, let's see, we want to say blank arrow S blank arrow S. Okay, so those are the level 5 objects. I'm a little confused here because I'm seeing things which aren't level, oh, no, what am I talking about? I'm doing arrow 5 here. Eek.
No, wait.
I got this wrong.
5 arrow.
5 arrow S blank.
Yes.
Okay, there we go. But that's very confusing because that's not a level 5 object.
No, but there is if you look on the bottom right.
There is an L.
Yeah.
Okay, so there's a level 5 L.
Because you can, because of the completion, you can go LR, 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 etc.
Okay, so actually what we want to do here probably is we want to actually keep that 5 because we're going to be looking at those things. I'm sort of hacking around the fact that cases is going to get confused if we say 5 arrow S blank.
Right.
Actually, here's what we want to do. We want to say, if we simply say X colon 5 arrow blank arrow X, that will work. Okay, so we've got this, and now what we want to do is we want to say the edge weights for those guys there, right? So we want to say annotation value oh, I'm confused how to do this. Well, we can make a subgraph. Yeah, we could just take a subgraph here. Take subgraph of this. And then we take the annotation value. Then onto this, we map hash and annotation value onto that. And then we make then we do a transpose.
Wait, don't we want to map onto the edge list? Or am I confused?
I don't think we need to.
Okay.
But I got something wrong here. So let's see what happened. So because what I'm doing here is I'm saying the annotation value, this is a subgraph.
Mm-hmm.
So that subgraph should have its annotation value Oh, it's edge weights. Eek. Now I'm confused. We need these edges here, right?
Right.
I thought we had state weights. I thought that at some point, by the time it's a branchial graph, the states have weights.
Yes, but that's right. So we could also include state path weights, and that would give the states weights in accordance with the sums of incoming evolution pathways.
Well, that's what we want.
Okay. Yep. Well, we can do that.
Okay. So up here we would say include what? State path weights. Okay. And now this pattern is going to be different because the vertex list is going to have a different form, isn't it? Or is it not?
No, because I think the weights are stored separately.
Okay.
I believe.
All right. So let's see whether that.
Vertex weight.
What's that?
Vertex weight.
So that looks good. Okay. All right. So those are the vertex weights of these vertices, okay, and the vertices of which they are the vertex weights are, I claim, vertex list of this thing here. Do you agree?
Yep.
So I think we can just say here, it's the annotation value of hash, comma, vertex weight. And then it is the vertex list of hash. Okay, and now we want to transpose that. Actually, we can just say, should we just get the L's and R's out here? Let's do a last slash at that. And then let's do a transpose of this. Well, we probably want to do a transpose. Sure, well, let's do a transpose. Okay, fine. So now we've got out the, actually let's package everything together. So this is now, that's the evolution there. So this thing here, with this inserted in the evolution, is we got the 5s have to agree, but we could do this. Let's just, make a slightly bigger one. Let's do 6s here. What did I get wrong? Oh, subgraph EVO there. Drat. Yeah, I have to make that a function. And then here, all right, subgraph function EVO. Close for the function, apply to this. Okay, that worked. Okay, good. All right, so now the question is, what is the ordering of the L's and R's? And I mean, so the naive thing we could do here, which I don't believe in at all, is to just say, I think we're going to get something from the entanglement map, so to speak, of the L's and R's.
Right.
But what we would get here, so this would be we just say bar chart of last slash at this. No, it is not a sinusoidal. It would be shocking if it was a sinusoidal interference pattern. But it is still entertaining.
I wonder what it is.
Yeah, I wonder what it is too. Let's take a look. Let's go a few more steps and let's see what it does. I think it's going to be, because I looked at these branchial graphs before, and they get it's kind of complicated, and it's kind of number theoretical what's going on in them. But I agree that this should have some limit, one would think. Let's see what happens. You know, it reminds me of when you do a substitution system and you look at things like the Fourier spectrum of the substitution system. This reminds me of one of those. But we can certainly, well, let's just take some, let's take some moving averages just for fun. So let's get data is this, and then let's say list line plot of moving average data comma 5, for example. And let's, no, it's too disgusting that this is looking sort of vaguely sinusoidal, totally coincidental. Okay, let's just try more smoothing. Yeah, well, whatever. Hard to tell what this is doing. Okay, but let's review what we thought this was, and let's see how we would get, you know, because what we want to do is map this onto a position basis.
Right.
Right. And what you were doing initially up here, when you delivered this to the beginning of this meeting, was it's as if the LLLLL thing is left propagation, so to speak. And the LR is kind of almost like the Huygens principle, so to speak.
Right, some kind of cross term.
Right, but it's kind of like a Huygens principle, as in from every point that the photon reached, the photon can go to the other point.
Right.
So what we might expect is that in the position basis, yeah, I mean, we might expect that it's an LR counting story. So let's just try that just for fun. Just see whether we can literally, if we position the thing not by, because the sequence that we had here was a sequence of L's and R's, right? So we're going from L, LLL, et cetera, et cetera, et cetera. So let's just imagine that this means left propagation. So that means it didn't propagate far to the left. So in other words, let's make L be -1 and R be +1, for example. And then let's just make the coordinate be the number of L's minus the number of L's plus the number of R's. Make sense?
Yeah, sounds good.
Okay, so let's go ahead and for this one here, let's do, okay, let's write a little function, RL coordinate, and that will be of a string, and that will be the very trivial counts of, well, actually what we could just do is to say count in characters of string, count of R minus count of L. I need a parenthesis there. Apply that to characters of string, yes? Characters of string. Actually, this is a stupid way to do it. I could just have said string count, I think. But anyway, it doesn't matter. This will work. Okay, so RL coordinate. So now what we're doing here is we're saying for this thing here, we are saying for each of these, oh, I see, we're going to have a lot of degenerate cases here. We're going to have to add up more than we thought we were going to have to add up. You see what I'm saying? Because what we're going to get here is instead of this, okay, so let's get this bunch of results. Let's say you do this for the 5 case. Okay, fine. So now here we would be saying RL coordinate of #1, #2, that thing triple at this. Okay, so there are our coordinates and our values. But now what we want to do is we want to aggregate the -2 values that we got here, right? Is there some clever way to do this with merge or group by or something?
Can we do gather by?
Possibly. If I could remember how that works, what does it do? So it's gather by, it's gather by first. Does it have a gathering function?
Good question. Hang on.
Why is this raft not coming up? So annoying. Oh, there we go. Gather sublists which the same as given. Okay, so we can just map it onto this.
Right.
Okay, so then we gather this, and then for each of these, we would say, so for each of those, all right, let me just get this in some semblance of something we can actually work with. So let's say gather by and now we're going to say, for each of those, we want the first of that. And then we want the total of last / at that. I claim. I think we want to map that over this. Okay.
Looking good.
Okay, now let's make a plot here. We want to sort by the first element, don't we? Okay.
At least it's symmetrical.
What's that?
At least it's symmetrical.
Yeah, I know. Well, that's good. But okay, so let's go here and let's try the case. Let's try a bigger case. Let's try 8, for example. What do you make of that? Hard to know. I mean, this is a very arbitrary choice of, if you're going to try and, imagine a diffraction pattern. Well, it's not an interference pattern in the usual sense, but I mean, it would be remarkable if this turned out to be that close.
Right.
But it is interesting that this has sort of most of its support is things that kind of go through the middle with about equal numbers of R's and L's.
Right, right. And there's periodicity, or some periodicity.
Which, who knows? I mean that periodicity is, if that periodicity is interference fringes, again, I need to get more hats.
More hats.
To eat. All right, let's try this case. How big is this? Let's see. How many nodes do we have here?
Well, we had path weights on the order of 20,000 in the last thing.
Yes.
That's already telling you something.
Okay, well, we managed to get it to compute, so that's a good sign. Really? That's interesting. I mean, it's basically the same curve. It's coming to a limit.
Right, right.
That's weird.
And yeah, so the peak, there is a genuine peak. It's not the same level as the things either side of it.
Well, but what is this periodicity nonsense? I mean, this is the 5, 6, 7, 8. Don't tell me it's Fibonacci numbers or something.
Yeah, there's some interesting number theory to figure out here.
Well, actually, this one has that one has a peak where that one has a trough. So it's not so obviously what's going on. Paul on a live stream is making a comment. It looks like a quantum walk graph, but I don't know what a quantum walk graph is.
I assume he means like a quantum random walk.
What's the difference between other than what's the difference between a quantum random walk and a non-quantum random walk?
This is a good question. So I assume it means that the randomness comes from some superposition that's evolved by unitary evolution.
It's proposing a Wikipedia page here. Let's see whether it.
Oh, so quantum walks don't converge to limiting distributions. That's interesting.
I see. So this is a discretized Schrodinger equation. The idea here is it's a discretized non-relativistic Schrodinger equation. I mean,
Right. Oh yeah, actually, these these do look somewhat similar.
Yeah, I agree that they look somewhat similar.
There's a thing called a Hadamard coin, which I assume is like a coin given by a Hadamard operator.
See, this is a different thing. The Feynman electron in 1+1 dimensions, which I also had a version of in the NKS book, that is a Dirac equation story. Oh, in fact, it said here that was for the Dirac equation, right? Yeah, that's much simpler for the Dirac equation. And I always found that the non-relativistic case really kind of confusing. Let me take a look here. This was a claim about, this was kind of the new value of each block is this. I see, that's just taking probabilities and with weightings. I don't know whether this is related. I mean, that's basically just taking a complex phase. Okay, well, anyway. All right, so question mark, any relation to quantum random walks? We should probably wrap up fairly soon here if we're going to do, well, we could take one, okay, so basically, what have we concluded here? We understand something, the thing we don't understand, and this model was, which you came with today, is a somewhat arbitrary non-space-time model.
Right.
To make it more
but where
spatial.
the multiway dynamics are presumably the same.
I agree. In branchial space, it couldn't care less. The problem is if we want to map it into something which looks like, physical space, that's more problematic.
Right.
So I think we need something, and that maybe brings us to the Bell's inequality discussion briefly. We need something where we're not looking at, it would be very cool to be able to do something where we can explicitly see a distribution of physical space. I bet there's a way to make this work. I suspect it's going to be a little bit more complicated than this. I suspect we're going to have to make...
we need a better coordinate system.
Yeah.
Amongst other things.
Yeah,
I think we're close to something here.
No, I agree. I think the surprise is, okay, so the important point is that the toy model, in the presence of either a completion or intrinsic causal invariance, that's allowing us the freedom to look at different foliations. And the foliations, so again, recapping, a scheme for measurement. We're making the claim that we can effectively measure, if we measure this, that will have consequences on subsequent time steps for what else we see happen. In other words, if we freeze this, that will have consequences. I think we don't fully understand the mechanics of those foliations. And somehow this reminds me of the whole Bohmian mechanics business. And I don't really know enough about that to understand that well. Do you understand that well enough? I mean, I wonder whether some of the sort of whole dynamics of some of the whole pilot wavy type stuff is actually a story of foliation dynamics.
Well, okay, so it's certainly possible to replicate something like a pilot wave by judicious choice of foliation, because basically, okay, so what happens in the causal, or as you say, the Bohmian interpretation of quantum mechanics, the reason why you're able to get violation of Bell inequalities is that if you consider the Schrödinger equation for some many body system, then you can get the guidance equation for the pilot wave, which is what guides the individual particles, and you can show explicitly by considering the complex wave function that the velocity of the jth particle depends explicitly on the positions of the ith particles for all I, right?
Okay. Yep.
So that gives you the non-locality that allows you to violate Bell's inequalities. Now we can have a similar thing here, where we can say we can construct a foliation that kind of that seals off a particular state, such that its dynamics is dependent upon the past history of kind of all other states.
Yes, I understand.
So we can construct something, but by just having a very high degree of curvature, we can construct something like a pilot wave that actually extends for the whole of branchial space.
That's interesting. I mean, it also relates, maybe our friend Gerhard at Hooft's cellular automaton quantum mechanics is related to this. If we could only understand what he'd done, we should just ask him. And let's see whether he can understand what we're doing. And then maybe we'll actually be able to communicate. Because I believe that he's doing something similar to this, where he's got, the whole structure of the state is part of the sort of story of the measurement, so to speak. In other words, what is happening here is the quotes non-locality, the globality of this story has to do with the globality of the reference frame more so than anything else, from what I'm seeing. That is, okay, one problem that we have is we do not have a theory of the dynamics of reference frames, because reference frames are for us arbitrary things, which then, but then given, it's given a particular, a particular slice in a foliation, there are implications for what future slices there can be. It's not determined, but there are implications. In a sense, there's a multi-way system of possible foliations, I think. So in other words, in fact, that's an interesting way to think about it. Given a multi-way system, there's a foliation of the multi-way system. Given that you make a constraint on one of the slices in the foliation, you do not determine the future slices, but you determine given any particular constraint, there is a multi-way system of future foliations, I claim.
Well, this is how we get the multi-way graph from the causal case, right? That different foliations of the causal graph correspond to different multi-way evolution histories.
But what I'm saying here is...
So then there's a higher order object where different foliations of the multi-way evolution graph yield to a second order multi-way evolution graph.
Well, hold on. The causal graph doesn't depend on the foliations, but going back from the causal graph to the original, to the successive steps in the multi-way graph, aka these branchial graphs, is something foliation dependent.
Hang on. I completely don't understand. So the foliation of the causal graph does matter if you don't have causal invariance.
Yes.
And so the multi-way system, each branch of the multi-way system is telling you about a different foliation choice of the causal graph in general.
Right. The point I was trying to make is...
So then you can consider different foliations of the multi-way evolution graph, and those will correspond to different evolution branches of a second order multi-way evolution graph.
Now I didn't understand that either. Look, the point that I was trying to make is these slices that we're making in foliations, right, are some kind of transversal to the multiway graph.
Right, right. And so the principle of multiway invariance is the statement that the combinatorial structure of the multiway graph doesn't depend on that foliation choice. But that, just as causal invariance doesn't hold in general, multiway invariance doesn't hold in general either. And so usually different foliation choices for the multiway evolution graph will yield different evolution branches in the second order multiway evolution graph.
Yes.
I'm just trying to make sure I understand what you're saying. I mean,
yes, but what I'm saying is, what I'm trying to do is I'm trying to make a theory of the consequences of a choice of foliation, right? The consequences of one slice, right? So there's effectively a time evolution of foliations, right? Given that you chose what one slice was going to look like, right? For example, you chose a slice that you chose, maybe it's two slices, I don't know, but slices where you froze that particular state, right? That choice of a slice in what will become a foliation affects, because of the partial ordering defined by the multiway graph, well, actually.
Yes, of course, which is right. So what I'm trying to say is you get the same issue in causal graphs, right? If you choose a particular slice in the causal graph, that will yield a different branch in the multiway graph.
Yes, absolutely.
Yeah. So all you're talking about is connectivity in the second order multiway evolution graph.
Okay, but hold on. This is the first appearance of the second order, and I want to understand what we're talking about here, because what I claim is that whether it's a causal graph or a multiway graph, this is essentially the beginning of something that I also was looking for in that distributed computing thing, of sort of the theory of possible foliations, right? Which we don't really have. Right now, foliations are added as a how you're making sense of the system thing, right? The foliations themselves, while it is not the case that any foliation goes, right? Only certain foliations are possible because only certain foliations are consistent with the partial ordering defined by the underlying graph. Right? So I'm simply asking the question, in the space of all possible foliations, what does the space of all possible foliations look like?
Right, I understand, and this was the point I was making in that meeting about, you know, the reason why in something like the proof object we can, you know, the best we can do is an after the fact report of the foliation choice, is because, you know, because different choices of foliations initially, you know, different slices will constrain future choices of foliations. It's, I would claim, impossible to get a kind of general language for describing future foliations.
Okay, that's a different issue. I mean, the thing I'm talking about now is just imagine the space of all possible foliations. Okay?
Right.
What is that space?
You mean foliations of the multiway evolution graph?
Let's say yes. I mean, we could also talk about all possible foliations of a causal graph.
Uh-huh.
Either way, I mean, we've got, maybe the causal graph is an easier case because we know there's a partial ordering there. And the theory of all possible foliations, the theory of total orders consistent with a given partial order.
Right. So the set of the space of all possible foliations of the causal graph is the multiway evolution graph modded out by branch-like separation.
Yes.
And
it's also, so we also know that in general, that it's like a function space where in general, some of those functions are unbelievably wild.
Sure. Right? So then there's a computability condition, or some kind of computational complexity condition you have to enforce.
Maybe, or some condition. I mean, you know, the question is really in that story of kind of, let's see. I mean, we have these wild pictures wherever they were. You know, I am so frustrated by the fact that this doesn't allow me to click on a single image that I see here and get to that single image. It's driving me crazy. See, we have got to fix this.
That's being worked on. It might be ready by tomorrow, just so you know.
Okay. That would be cool. Oh gosh, where is it? I am looking for that it, or is that something completely different? You see, that's completely different. Do you know what picture? I'm looking for this picture that shows the possible total orders consistent with the given partial order. It's a lovely picture, except that I now can't find it. So frustrating. It's one thing if one's never generated the picture. It's another thing if one's generated the picture but then can't find the picture. I think I've looked for this picture at least twice before in one of these. No. There it is. That's what I was looking for. Okay, so look, this is a very trivial partial order, right? And we know that these are, this is the set of possible foliations for a very trivial case. So it's a big, wild, complicated set. But the question is to characterize that set of things, because that is giving one, with some constraint that might be the observer sophistication constraint, so to speak. But I mean, my question is, look, this is the analogy with thermodynamics, effectively, that there are only certain kinds of measurements that it is plausible to make. And so, for instance, in the quantum case, one of the things we wonder about is there might be certain measurements. Okay, so here's a question. Imagine you could pick any foliation, any quantum observation frame. I think it's kind of obvious that you can get things that seem very much like they don't follow quantum mechanics, or they don't follow what we would expect. And my guess is that is similar to being able to pick weird coarse graining schemes in statistical mechanics that don't do what you would expect. But I'd just like to understand, what is the condition? I mean, in the case of statistical mechanics, we understand, well, at least I think I understand, what roughly the condition on how you become a plausible observer is. And, the question of how that exactly relates to what you would see, how much fluctuation you would see in entropy increase and so on, we don't really know. Interesting question. I mean, an interesting question whether there's a relationship between the somehow the level of computational sophistication of the observer and the degree to which they can act as Maxwell's demons, so to speak. In other words, if you think you're seeing entropy increase, to what extent can you fight entropy increase by a certain level of computational sophistication? What's the analog of that in quantum measurement?
Right. Well, I mean, it's perhaps easier to think about it as an analogy in general relativity, where you're saying, the fundamental problem in general relativity is you're an observer and you're seeing the evolution of a bunch of clocks, and you're trying to compute a gravitational field configuration that's consistent with that evolution. And so you are constrained as that observer that your computation has to be at least as sophisticated as the computation being enacted by those clocks.
Yes.
Right. If you want to be so any foliation for which that isn't the case is a non-computable foliation from the perspective of that observer.
I know, as we've discussed a bunch of times, and you were about to write some lovely formal paper showing what the consequences of that are.
Right, which I still intend to do.
And what do you think is going to happen there? I mean, that is that given this computability thing, your claim is that if you make this computability constraint on effectively the allowed foliations, what is that going to imply for general relativity? It's going to imply a bunch of things about this hyperbolicity business.
Yes, and I think my conjecture, I mean, obviously we don't know exactly how this is going to work out, is that this is basically what will happen is that at least in some cases, there'll be a correspondence between energy conditions in GR and these computability conditions. So, things like the null energy or the weak energy condition, things about statements about like, okay, the null energy condition, which is the statement that if for every future pointing time-like null vector, the tidal tensor has non-negative trace. That's a purely a purely geometrical statement about space-time, but it places certain constraints on what energy configurations are allowed in that space-time. In the same way, if we place certain conditions on the computability of the observer, I think it's going to place certain conditions on the kind of geometric field configurations.
So let me play that back. So I mean, the claim is, a bunch of those energy condition things imply, as the star collapses, the energy conditions basically say there's inevitable singularities and things like this. So one Maxwell's demon type thing that you could do is there a Maxwell demon that could be inside the collapsing star that's very carefully throwing pieces of mass around in order to prevent the singularity from occurring?
Right. Yeah, and the argument would be, just as in the Maxwell demon case, that eventually that demon has to basically have an infinite mass. That if the demon wants to continue doing that, its investment of energy has to be sufficient that it basically itself becomes a singularity.
Oh, I think that argument for the Maxwell demon thing is a pre-computation argument, which the energy argument is crazy. I mean,
no.
Go ahead.
I'm not saying the Maxwell demon argument is the energy argument. I'm saying, so in the Maxwell demon argument, it's computability. It's computational. Some kind of computational capacity argument. My statement is that in the general relativity case, it is an energy argument, because that's the quantity that's associated with an elementary causal edge.
I understand that claim, but let's just walk through this for a second. So the question is, can you avoid the singularity theorems by essentially a Maxwell demon, mass redistributor? That's basically the question, I think.
Right.
In other words, you've got a bunch of GD6, and in the natural course of things, they just go splat into one point, and they inevitably lead to a singularity.
Mm-hmm.
So, but could you consider an initial configuration of masses so carefully arranged that you avoid that? Or even worse, something where, as the star is collapsing, the civilization that lives around it is, carefully computing where to put each little tiny piece of mass in order to prevent the collapse.
Right.
Okay, so let's walk through whether that's possible. So, I mean, your claim is that the impossibility of doing that is essentially a computational impossibility. And I bet that's right.
Right.
I mean, in other words, you could imagine, is it obvious in some sort of, I don't know, it's probably a generalized functions mass distribution thingy. I mean, is there a mass distribution that you could imagine that would not, that there must be, because there must be a way to still satisfy the Einstein equations, but not, there's an energy momentum tensor that's moving things around. So it's not like that's deforming the trajectories of GD6.
Mm-hmm.
Right. Yeah, it's kind of cool. Okay, so let's understand the analogies. So one analogy is the Maxwell demon in the thermodynamic case. Another analogy is the dying star civilization trying to prevent black hole formation. Right?
Right.
It's basically that case.
Yeah.
Okay, what is the quantum analog of that?
So I think the analog of the demon in the quantum case would be something like you have a person, instead of a person with a bunch of clocks, you've got a person with a bunch of interferometers. And they're trying to come up with a branch-like foliation that's consistent with the evolution of those interferometers.
Yeah, I understand that. But what does that mean? What is the analogous thing? What is the thing you're trying to prevent? I think you're probably trying to prevent
a pure state, a qubit.
Is it a pure state, or you're trying to prevent a classical state?
You're right. You're trying to prevent something that appears to be evolving classically.
Right, and you don't succeed in doing that because which is the same thing that you're saying with the qubit, because basically to say you're preventing something. Okay, so this is fighting classicalization, so to speak, aka fighting decoherence and so on.
Right, right. Your error correcting codes eventually take so much computational power that it's no longer possible.
But what is, okay, so, but it's a little bit different because the singularity theorems say you're going to wind up in this state that is, in which all the geodesics converge. What is the analog of that here?
Well, convergence of geodesics is completion.
Okay.
Right. I mean, you're saying
or resolution of branch pairs or whatever.
Right. If you have sufficient curvature in the branchial hypersurface, then it's inevitable that branch pairs have to resolve.
Yes.
So the state in that region looks classical.
You're saying when the branch pairs all resolve, then it's like classical evolution. That's obviously true.
Yeah, you just have a single multiway thread.
What you're saying is the analog of the singularity theorem, which says the geodesics are converging, is the convergence of branch pairs, and which is the analog of that is classicalization. So you're saying that the analog of the civilization, the dying civilization. Okay, the analog is. I'm sorry, I can't help the. This is what I get for doing these live streams for too long. The analog is the quantum computing company that is desperately trying to keep its computer quantum, even against all odds, like the civilization around the star that's turning into a black hole. So their goal is keep the thing quantum. Don't let it become classical. Don't let the branch pairs resolve, basically.
Right, right.
So, and the claim is that gets more and more computationally difficult, which is sort of bad news for, if you think you're doing quantum computing, the fact that you're not quite refrigerator, but you're sort of qubit maintainer of qubitness, so to speak, has to get more and more and more elaborate, which is what one sees in practice. So, to be clear, that the analogy then is that is the that's the analogy. So let's just line these up for a second, okay? So in the case of thermodynamics, what we're saying is, in the case of thermodynamics, you're getting to equilibrium states, and your daemon can't prevent you from getting to equilibrium. Your daemon would have to decrypt everything to prevent equilibrium.
Right.
In the gravitational case, the daemon's goal is to prevent formation of singularities. I don't quite understand. I see. In the thermodynamic case, equilibrium, this is very beautiful, actually. In the thermodynamic case, equilibrium is the emergence of bulk quantities. That is, in equilibrium, all you need to say is, my box has a temperature of, 30 degrees or something, right? Out of equilibrium, it's like there's lots of singing and dancing going on in the box, and there's a lot more to say about what it's doing than just to say it has a temperature of 30 degrees.
Right. But gravitational equilibrium is black hole formation. Exactly.
So the singing and dancing that happens in the civilization around the black hole is all the things you can do that aren't just the uniform, there is a black hole there, and that's all you have to say about it. So similarly, in the quantum case, the singing and dancing, so to speak, is the quantum processes that have not classicalized, where the branch pairs have not resolved.
Right.
So you know what I'm going to ask about next.
Rulial?
What's the analog of this in Rulial space? Okay, so let's think about that for a second.
Right. It's that the Inquisition has to put in an arbitrary amount of computational effort to prevent Galileo from forming his Rulial black hole.
Yes, let's think about that claim. Okay, so the issue is, in that case, the geodesics in Rulial space, which we do not understand very well yet, is the formation of Rulial black holes inevitable? Are there singularity theorems? Okay, so here's another question. What's the analog of the singularity theorems in quantum mechanics? It's
Right,
probably some inevitable decoherence result.
Yeah, it's a statement that once your entanglement rate, exceeds some particular value, then classicalization is inevitable, which is kind of what we expect from decoherence.
Right. I mean, so once the entanglement rate, so what that's saying is, when the entanglement rate is above some value, the effect of the environment is affecting you to the point where you can no longer maintain where you're forced to be kind of at equilibrium with your environment.
Uh-huh.
That's a little different from the general relativity case, isn't it? In other words, what's the... Oh, I see. No, it isn't. No, it isn't. No, it isn't. Because what's happening is you're pulling in, by being at equilibrium with the environment, that's the black hole ate everything.
Yeah, right. Your singular, gravitational entanglement is like, singularity accretion.
Right. So the gravitational analog of entanglement is just the merging of geodesics into the black hole.
Right. And by the way, this answers, I think, one of the questions that came up in the Q&A earlier about, do you have a quantitative model for the evolution of scientific progress or something? And that is that is geodesic merging into Rullier black holes.
All right, let's look at that for a second. Okay, so the claim is, in Rullier space, the first question, we don't really understand the analog of the Einstein equations there. We don't really understand the notion of a geodesic there, where... What is a geodesic there? Geodesic is somehow... What the heck is a geodesic there? I mean, it's the... you could argue it's the time evolution of a state of knowledge, and the foliations are the way in which you describe that knowledge. So, for example, you might say, the fact that the world is made of identical objects, which was represented, or the fact that computation is a thing that was represented in terms of souls back in the day and is now represented in terms of computation, that those are two different... It's the same sort of geodesic representing that knowledge, but it's differently coordinatized. It can be differently coordinatized. There may be one possible model. But in that picture, what is the analog of mass in Rullier space?
Well, time complexity was my conjecture yesterday. Right, because
there's a bundle of algorithms.
The flux of causal edges in Rullier space is some measure of activity for a particular rule, a particular algorithm.
Let's just write down a little conclusions here. Okay, so I want to just, because otherwise I'm going to forget all these things. Let's say, what are we going to call this? What is this? This is what on earth is this?
Systematic meta-philosophy.
Let's start with meta. Let's just call it meta. I don't know what else to call it. Okay, so let's just write down what we think we understand here. So, in thermodynamics, okay, Maxwell's demon attempts to prevent equilibrium, aka thermalization, by putting in computation. Why on earth is that not a spelling word? That needs to be a spelling word. Okay. Attempts to prevent equilibrium, i.e., prevent convergence of states to be purely described by bulk quantities. So the analog, okay, so in general relativity, the you know, the dying star civilization attempts to prevent convergence to a black hole, convergence of JD6 to a black hole. And the quantum case, the quantum computing company attempts to prevent convergence of essentially JD6 in branchial space. Well, let's see, JD6 to a classical, in branchial space to a classical outcome. And that is, and so the claim is that will tend to happen, this will happen inevitably in the same way as the singularity theorems in general relativity, if the amount of entanglement is too high. All right, so now the next case is the Rullial space case. And your claim is it's all about the Inquisition, but let's try to get, I don't think it was quite the Inquisition, well, I don't know what it was in those days, but anyway, Cardinal Bellarmine or whoever.
Right, right. So my point was simply that there are pockets of reducibility, right? So there are sort of inevitably event horizons in Rullial space. But you can try and construct a foliation that pretends they're not there. But to do so requires over time, and to sustain it over time requires an arbitrarily high level of computational effort. So
you're saying
to deny the existence.
Okay.
Yep.
There exist Rullial black holes which correspond to pieces of computational reducibility. Okay, now your claim is, what is your claim? Your claim is that you can make a foliation which denies the existence of these. Or alternatively, but I want to see it from the point of view of the sort of the controllers of the JD6. What are they trying to do? They're trying to prevent, they're trying to keep things in the computationally irreducible area.
Right.
So the demons are trying to keep JD6 away from Rullial black holes.
The obscurants.
Yeah, away from the enlightenment, so to speak, of Rullial black holes. Or more particularly, we really have to make Rullial a spelling word here. More particularly, as soon as you're in a Rullial black hole, you're essentially able to jump ahead, and that represents a piece of understanding of the world, so to speak, that is not irreducible.
Right.
And see, the thing that surprises me a little bit, and I don't quite understand yet, is the inexorability, the analog of the singularity theorems, isn't what I would expect in Rullial space. Because what seems to happen, what happens is it feels, okay. So here's the issue. In thermodynamics, you might think everything's very complicated. But instead, we can talk about equilibrium. So we can simplify, we can make a reducible description. In a sense, equilibrium is the computationally reduced description of a gas. Right, and so similarly, in other words, by this convergence, and arguably, a black hole is the computationally reduced description of the galaxy. By saying a galaxy, black hole is, that's the thing. If the galaxy turns into a black hole, you don't need to say nearly as much to specify things about the galaxy. You're not talking about all those different stars and so on. You're just saying it's a black hole with a mass and angular momentum.
Right. Yeah. No hair is the ultimate compression algorithm.
Right. So no hair is the analog then of which I guess is something one sort of knows from black hole thermodynamics, is the analog of thermal equilibrium. So now what's the analog of no hair? So the analog of no hair here is no quantum phases.
Right. You just have one eigenstate.
Right. Okay. So now in the Rullial case,
you just have one algorithm.
No, I mean, the point about a Rullial black hole is it allows you, the point about reducibility, it allows you to jump ahead without seeing all that detail.
Right. But so what it's saying, when you have geodesic convergence in Rullial space, I would argue what it's saying is that the analog of the no hair theorem is the statement that basically everything within that event horizon is described by a single algorithm, or can be described by a single algorithm, a single rule.
Yes, I agree. So but that's saying once you're in the superhighway of that Rullial black hole, you don't need to take all the surface streets of computational reducibility around it.
Right. You just have to you only care about the singularity.
So okay, so do all the irreducible things, all the irreducible computations around it. But so what's the analog then? Let's see. The thing that surprised me, okay, so what will cause you to inevitably fall into a Rullial black hole? It's somehow that the only thing that happened in the universe is something, the only thing you care about. Look, the fact is, a Rullial black hole is something like the statement, the fundamental law of the universe is x equals 0, but you don't really necessarily know what x is.
Right.
In other words, it's a trivialization. It's a place where the thing you choose to look at in the universe trivializes what the universe does. So the claim is the Rullial black hole corresponds to a sort of a trivialization. It corresponds to slicing off a trivialized version of the universe. Trivialized. So in other words, it would be like saying, you've got an irreducible computation to do. Yeah, it's like saying this Turing machine is doing something very, very complicated, but all I care about is the fact that its head visits the origin.
Right.
And if that's all I care about, that corresponds to a Rullial black hole, because I can just jump ahead and I can get the answer to that more easily. I don't have to go and look at all the fine detail. I mean, like, take Rule 30, for example. If I say all I care about is the width of the Rule 30 pattern, I don't need to go compute every detail of it. I can just get to that answer immediately.
Mm-hmm.
You know, I mean, okay. Let's just see here. So I still don't quite get this. I don't quite get what. So the demons, I see. Okay, look. The demons are trying to prevent trivialization in the following sense. Yes. Okay. What you're trying to prevent is that the only thing you care about is something which is ultimately trivial. In other words, so what you care about is defined by the foliation. But I think this is the right thing. I think what's happening is, you know, demons are trying to prevent trivialization, as in other words, they're trying to prevent that the only thing your foliation notices is a trivial feature of the universe. Let's think about that for a second. Well, again, think about it in terms of bundles of algorithms. Yeah, I really think that these black holes, yeah, they're looking at features of algorithms that are somehow trivial features, don't require going through the whole computation. I mean, it's like in thermodynamics. What you're saying is, if all you care about is the equilibrium features of the system, then you only need to know the temperature and pressure. That may not be enough. You might need to know the fifth-order correlation functions between the atoms.
Right. Okay. I don't disagree with any of this, but I'm not. Okay. My way of thinking about this would be more like, you know, you want to trivialize something, so you want to have some way of computing the overall width of Rule 30.
Mm-hmm.
So Rule 30 is one way of computing that, but the fact that you've trivialized it means that there are many other rules that will also compute that same thing. So in other words, you have computational equivalence between a set of a collection of algorithms, and therefore you have a convergence of geodesics. But here's what's going on: the demons are trying to construct arbitrarily weird description languages that make it seem as though those algorithms aren't really the same, that they're not computing the same thing. But the statement is, if they're truly computationally equivalent, they can't do that forever, right? If they're truly computationally equivalent, even if the demons try to design arbitrarily pathological description languages, eventually the fact that they're computationally equivalent will become manifest.
Well, I think you're conflating a few different things here. So, I mean, I think this point about there are algorithms. Okay.
What am I confusing here? I mean, isn't that the notion?
What you're confusing? Because I'm confused by what you're confusing. To quote one of your famous lines.
Right. Okay.
I'm okay, but I think your point about if all you are trying to compute is the width of Rule 30. Actually, okay, let me show you an example, which I think might be instructive here.
I mean, that's one way of thinking about computational reducibility, right? It's that you're increasing the size of the equivalence class of algorithms.
Sure. Right, so, okay. So computational equivalence is defining, well, our translation is defining a certain cone of equivalence, a certain cone of equivalent algorithms. Here's the thing I wanted to show. Let me try and pull it up. Yeah. this weird thing, okay? So all of these cellular automata are doubling the size of their input.
Right.
Okay. Obviously, some of them do it in a ridiculously ornate way.
Mm-hmm. Right. So those would be geodesics that have very long, that appear not to be geodesics because of some weird curvature of the space. They appear to have very long trajectories, but they still end up at the same place.
Well, there's something useful here. I don't quite get it. Somebody is asking on the live stream, what is a rule black hole? So the idea is, in this space where you have a rule space multiway system, where every node of the multiway system, every branch in the multiway system can correspond to a different rule being applied. That's what we're talking about. And then a black hole there is something where let's see I mean, one definition of it is just this thing where there are incoming edges and no outgoing edges. But I think there's a better way to think about it. It's also something where its only foliation is one that freezes time, or in other words, where you can get to the answer it's actually confusing to me that this. Now that it's a bad sign when I try to explain this concept that I thought I understood, that I get confused. Jonathan, do you want to try and unconfuse this?
Not particularly.
All right, I think we need to. Okay, there was a question here on the live stream from Marcos. Are time crystals related to the question of feasible foliations? I don't think so, because time crystals are more like, for us, are more like closed time-like curves. I mean, a time crystal is more like something where there is inexorable repetition of something. I think.
Although those kind of harmonic oscillator things we were looking at in multiway graphs, conceivably could be thought of as time crystals.
Absolutely. Yeah. Planumber is saying all changes of rule lead to the same final rule. It's not quite that. So Quatonian is asking, what is time in rule space? The good news about all of our models is time is always the same. That is one of the things about all these things, general relativity, quantum mechanics, and so on. The time is the inexorable operation of computation, which is otherwise known as following causal edges in a causal graph. That is what time is. So time is just let's see. So here, yeah, I mean, so in the black hole case, yeah, we need to understand more about this. We need to understand more. I mean, honestly, if we can, if we can unify the ideas of thermodynamics, general relativity, and quantum mechanics, we're doing okay. I would say that's a partial credit type situation. Being able to, this final unification is an attempt to unify the space of all possible rules in the way that we are attempting to unify in thinking about general relativity. We're unifying, in a sense, I mean, in some sense, that's about sort of translation in space. This is about change of quantum states. This is about translation in rule space, where we just need to understand this more. It needs to be need to understand it more. All right. Well, listen, we only got through half of what we had hoped to. We hoped to also talk about Bell's inequalities, which we didn't manage to do here. And you had prepared something about Bell's inequalities, which is either going to make Bell's inequalities seem trivial or is going to just make us more confused. And I think the real question here is to understand what is the essence of Bell's inequalities. And, because Bell's inequalities are usually talked about in terms of photons or electrons or something like that. And the question is, can we understand them at this more bulk level, just in terms of the structure of quantum states? And I think we have to leave that for another time. Calais is asking, why is time needed in these models? Time is what, the progress of time is the story of what is happening in the universe. That is, if it wasn't for time, time is the sort of progression of things that happen. And if you're asking, could you instead define something, just boom, here's all of time, here's the whole history of time. The whole point is you can't do that, because that's like asking, to know the whole history of the universe is to solve an undecidable problem. Because the whole history of the universe, if it's infinite, is asking you to immediately resolve this undecidable question. And the whole point is that if one is thinking about the progression of the universe as a progression in there's time really means something in this model because it is computation, and you can't just jump ahead and produce a kind of this perfect crystal of everything that happened in space-time, because that crystal is by definition undecidable to produce. Now, you could start asking, could there be a hypercomputer outside the universe that's making that? Well, yes. But I don't know, at that point you might as well describe what's going on in terms of the computation that we understand, rather than just saying there's a hypercomputer that stamps out the full space-time history. Jonathan, do you have any words of wisdom on this topic?
Sure. So, yeah, the one thing I would add to that is that there's a more kind of physical reason why it's really important that there's computational irreducibility, for the in the sense that Stephen said, that the fact that time plays this fundamental role because it's the thing that prevents you from shortcutting the outcomes of computations, is kind of important for giving us the concept of objective reality in these models. Because as we've been discussing today, that there's a lot of stuff that depends upon choices of foliations, either of causal graphs or of multi-way systems or of Rullial space or whatever. But the point is that the one thing that always gets preserved in all of those different foliation choices are the edges, are the time-like separations between states or events. So that, which gives you a way of having a notion of an objective reality that is consistent between different observers, either different relativistic observers or different quantum observers, or people with different description languages. And if if time didn't have that privileged position that computational irreducibility gives it, one would therefore have effectively no concept of objective reality, because there would be no features of the causal graph or the multi-way system that would get preserved under different foliation choices.
Well, this, if there was no time, is kind of the whole thing collapses, right? Because if there's no time, there's no notion of anything happening. So there's no variation of possible realities.
No, I'm not saying if there were no time. I'm saying if time didn't have, computational irreducibility gives time this privileged position of having a directed edge where everything else can be undirected, right?
Yes.
And my point is, if that weren't the case, then there would be no constraints about how you foliate causal graphs or multi-way systems.
That's true. That's true. So your point is that the fact that is a directed graph forces. So another way to say it is it forces there to be a definite sort of narrative story of what happened, whereas otherwise you could just weave in and out and back and forth and so on. Whereas, yes, but exactly. there's a flow to the whole narrative that is forced by the sort of inexorable directedness of the time.
Exactly. It gives one this notion that there is an objective reality that's described by the partial order, even though, as you showed in those pictures, right, there are several total orders that can be consistent with that. So aspects of observation can depend on observers, but the objective reality of the partial order is preserved.
Well, yeah, right. And the fact that there is computational irreducibility and that it's not all reducible means that there is a story to tell. In other words, if it was all reducible, that whole partial order would just collapse. There would be no story. There wouldn't be anything that actually happened. Nothing interesting would ever happen, so to speak, because it could all be compressed to, the answer is 42 or something.
Right.
But let's just take a look at these couple of last questions, then we should wrap up here. There's a question here, does that imply there's a universal clock cycle? Absolutely not. The whole point is that in these models, the updates can occur, any update that is consistent with the rule can occur whenever and wherever, so long as it has the inputs it needs to happen. In other words, so long as then it can occur. And having the inputs it needs means that the things on which it causally depends have already happened. And that's to say there is a time-like edge that is kept in the correct order. But it isn't the case that there's absolutely no universal clock. And in fact, that's why what we're doing, the perception of a universal clock comes about because of the foliation that we choose to use to describe, to take from our causal graph, which is the only sort of reality that we have, to extract from the causal graph. We say there is a foliation in which there is simultaneity, in which there is we could choose to do that in certain cases. We can't choose to do that if we have black holes running around and things like that. We can no longer choose to do that, but we might be able to choose to do that. And but that's merely a choice. It isn't the actual underlying reality of the system, and it's not always possible. So you're saying, Brian is saying, computational reducibility is an emergent property of time. I would say it differently. I would say that time is an emergent property of computational irreducibility. That is, that the perception that there is a time, that things do not compress into everything instantaneously happening, is a consequence of the fact that there is computational irreducibility, which prevents the perceptive compression of time, so to speak. We can't successfully say, we can't use perception, or our process of perception can't successfully compress time to nothing. That's the same thing we keep on saying with these different sort of foliation choices and so on, that our because of computational irreducibility, time has a real extent, so to speak. Time is not compressible to nothing. All right, interesting stuff. Well, good. We made some progress. We got more to do, more black holes to find from yesterday, more quantum effects to find from today, but definitely some interesting things here. Okay, actually, so one last point here. Time is not simply a measurement of change. Time is the fundamental force of the universe. Yes, that is correct. Time is the thing that the passage of time is the real story of what's happening in the universe. The idea that you can, quotes, move through time is a wrong idea. Time is an inexorable thing that happens in the universe. It's not something like space where you can sort of make the choice to move through it. You cannot do that with time. The attempt to make time seem different is an attempt to pick a different foliation, which is a different description of what's going on, but there are strong limitations on how different that description can be. And in the end, there's sort of an inexorable, this inexorable flow of time is an inevitable feature. And that's the fact that this model is a fundamentally computational model, and given that it's a fundamentally computational model, it fundamentally involves computational irreducibility, which implies effectively that time is an emergent feature of the model. I mean, that's kind of the logical flow, I think. And I would claim that my claim about sort of the history of physics here is the wrong turn that was taken, which caused this idea, this aspect of this idea not to be realized, is this fact that mathematically it was convenient to package space and time together. An idea of Minkowski's from, I don't know when, maybe 1909 or something, around that time, to sort of package space and time together and never talk about them separately. Now, interestingly, in this discussion today, we've been talking about the possibility that in quantum mechanics, a wrong turn was taken in packaging together the norm and the phase of the quantum amplitude, and that is another interesting idea that would be, I mean, in a sense, it is a lesson for us that undue packaging of disparate concepts confuses things, because you think you've made an abstraction, but actually you made a wrong turn. So in other words, it's like, I'm going to give a silly analogy for people who are computationally oriented. In Unix, the idea that devices are files, for example, which is at some level a good idea, at another level is kind of a bad idea because they behave in very different ways. Like you can seek to the end of a file, but you can't. That's a story like computational irreducibility. A file is already just there, but a device that is reading from a terminal or something is, that there is an inexorable. You have to wait. You have to block to wait and read the whole device. Read everything from it. But I mean, that's an example where a unification was made that is interesting, but leads one into a certain amount of trouble. And I think that I mean, in the what I do for a living of language design, a lot of that is about what unifications can you make that don't lead you into trouble. And I have to say that it is interesting, and it makes one wonder if there are other things, the packaging of space and time, the packaging of norm and phase in quantum mechanics. I just wonder whether there are other things like that have been done as a matter of convenience in a particular slice of a mathematical theory that will turn out not to be correct. I mean, I think there are a limited number of descriptions of, well, anyway, that's another, I mean, it's always interesting to think about like, for example, for those who sort of like kind of the meta theory of how things get figured out. I mean, the very form of thinking that we're doing here, of trying to make these analogies between thermodynamics, general relativity, quantum mechanics, is, I think, an interesting, that's a sort of meta level of trying to figure things out. And I think similarly, this meta level of what has been packaged that shouldn't have been is an interesting sort of meta level of trying to figure things out that perhaps we need to look at some more. All right, we should wrap up here. We may do another working session tomorrow, perhaps. I'm not sure. It'll be later in the afternoon. If we do tomorrow, I remind people who are interested, I have signed up to do a Q&A for kids about how things work, which I suppose could include the universe if people ask about that, but I was thinking it's more like things that us humans have created in technology and so on, or maybe things in science. Oh, Monday. Oh, that's interesting. We have a discussion with Jim Gates about his ideas about adinkras and so on. That will be actually our, gosh, has that come up so quickly? It will be actually our first kind of interview discussion here. All right, something to look forward to. Okay, well, thanks a lot, guys. And thank you to people on the live stream. And we'll see you another time.